So in a previous video, we derived the format for a spring problem for something that has no damping, a mass attached to a spring, and we got some solutions that look like sines and cosines. And we thought, wouldn't it be amazing if we could, maybe you didn't think, but I thought, and other people have thought, wouldn't it be amazing if we could just look at that equation and know exactly what the graph is going to look like? And the answer is we can do that. All right, so let's take a look at how that would happen. So we are going to start off and do a fun little derivative or derivation because derivations make us better people. All right, so we're going to arbitrarily let this thing called omega equal the square root of k over m. Why? You'll see in a minute. You'll thank me later. K over m. So that means I can rewrite this as x double prime plus omega naught squared x equals 0. So I can write the characteristic equation r squared plus omega naught equals 0 squared. So that means that r is equal to plus or minus omega naught I, meaning that I can write a solution in the form of some unknown a cosine omega naught t plus b sine omega naught t. And isn't that so much better? You're like, no, I just did that. I know how to do that. Okay. Well, what's kind of fun about this is we are going to randomly define stuff. And it's not really randomly. It's all going to work out in the wash. There's probably a fancier way to derive this. Randomly do this. We're going to randomly do r is equal to a squared plus b squared. So r squared is equal to a squared plus b squared. So basically saying we're going to have something that is equal to, and if I did it the way I was originally intending like this, then we're basically saying that if we have things going different directions, that r is this magnitude of their resultant kind of thing. We are also going to come in here and define b over a as being equal to some kind of tangent phi. Why? Because it makes us happy. So we're going to call that sine phi over cosine phi. And because I'm kind of awesome at algebra, I can say that b is equal to a. Yes, sine going down. Actually, I want to go ahead. It doesn't matter, but my notes are different, so I just want to be consistent. That a is equal to, let's see, b times cosine phi divided by sine phi. All right, and I know that r squared, I'm going to go ahead and do more fun stuff. R squared is equal to a squared, but this is a squared, plus b squared. Yay! Now if I multiply the whole thing times sine squared, just to get that thing out of the bottom, we've got sine squared r, b squared, cosine squared. Look at all this squared stuff. Squared stuff. And what's really cool about this, if you look over on the right, is I can factor out a b squared, and I've got sine squared plus cosine squared. And that's really exciting because that is equal to 1 because of trig and stuff. So essentially what I'm able to figure out is that b is equal to r sine phi. Okay, so if I know that b is equal to r sine phi, I can say r sine phi cosine phi over sine phi. So that's r cosine. So I can say that a is equal to r cosine phi. You're like, I don't care. Sure you do. Everybody cares because this is important. All right, so I now have values for a and b out of some random thing that I made up. Okay. So let's go ahead and plug these in. It'll be awesome. You're going to love this. So I have that a was equal to r cosine phi. And then cosine omega t, and b is r sine phi times sine omega t. You're going to be like, this isn't helpful. This is pretty much the exact same thing we already had, except even worse. Yes, absolutely. Except that you might remember that there is a little theorem-y thingy that says the cosine of a times the cosine of b plus the sine of a and the sine of b times the sine of b is actually equal to the cosine of a minus b. Yay! Awesome! Okay, so this is actually very helpful because this is exactly what we have. So we can rewrite this as the sine of cosine, or r times the cosine of phi minus omega t, or since cosine is an even function, then we can actually rewrite it as r cosine omega naught t minus phi, like that. Now, this might not look like anything, but this is actually something special. This is something that deserves flowers and rainbows, and what else does it deserve? Flowers and rainbows and kitty unicorns. Unikitty. I always liked Unikitty. This Unikitty is a angry kitty? Maybe he's not angry. No, he can't be angry because he just solved this problem, so he's kind of like a happy kitty with a, I don't know, a flower foot and a rainbow body and a tail made out of, I don't know, possum tail. Okay, there's my kitty. Anyway, my kitty's super happy about this amazing derivation that I have put together. Okay. Now the reason that I care, and that kitty cat cares, is because if you look at this, and if you know anything about trig, which might be pushing it at this point, but if you know anything about trig, we can look at this, or even graphs in general, this is going to be the amplitude, right? And that should make sense because sine or cosine is going to go between 1 and -1. So this value here is either going to be as a max of 1 to -1, like that, which means that r times 1 would be as high as it could possibly get. So that would be the amplitude, or the height, of our graph, right? Cool. Now, the other thing that's really cool about it is, if you, again, know anything about, graphing transformations, is that whenever we subtract something from the inside of a function, it kind of does the opposite of what we expect it to do. If I have a minus phi, that actually means that we're shifting to the right by phi. So we're actually shifting the graph right by phi, which means if cosine is normally supposed to be like here, we've actually shifted it to the right by a certain amount, which means that it's really this far over. So now what we can do is, if we can rewrite our constants, or take the square root of the sum of the squares of our constants, we can get the amplitude. And if we take the inverse tangent of our constants, as long as we put them in the right order, then we can get the phase shift. And this is just so cool, because now I can solve this problem. You could be like, well, what does that look like? And be like, bam, amplitude, phase shift. I can tell you absolutely everything you could possibly want to know about the solution. It's also cool because you can actually find the frequency. So we know that the period, if you have a period t of this graph here, the period t is going to be equal to 2 pi, or the omega t, omega times the period would be 2 pi. So I can get the period, and I can get the frequency, because the frequency is just 1 over the period, so I can get the frequency as well. So putting a solution in this form just really gets me this absolutely fantastic version that actually makes sense. So we did a problem in a previous video where we had a solution that looked like this. And we said, okay, well, that's perfectly fine. And then I graphed it on a calculator, and I told you that, it had a max and a min of like 1.55, but it intersected here, and so it was a little off. So the question is, could we use so this form that we just did is called the amplitude phase form. So amplitude phase. So if we rewrote in the amplitude phase form, we would actually have not needed to graph that by hand. So we know that our resultant, or our amplitude, is the square root of the sum of the squares, like that. And we know that phi is equal to the inverse tangent of the cosine, or the sine term, b, over the cosine term coefficient, a, or the inverse tangent of -1/4. Got it? So now let's go plug this into the calculator and see what we get. Go back. So let's do the square root of 1.5 squared plus 3/8 squared. Thank you. So we've got 1.55, so that's the same amplitude that we got before. And then for our inverse tangent, I'm in radians. I had to be in radians to graph it, but I'm going to make sure I switch over to degrees. For the purposes of phase, we almost always express phase in degrees just because people understand that better. So negative 0.25. We have negative 14 degrees. Now, it's actually important to make sure that's the right, the right coordinate system, the right quadrant, because basically what you have is you have the inverse tangent of y over x. So if you're doing the y, that would be, or y over x, that would be x, y coordinate would be 3/2, negative 3/8. Now the reason it matters is because your calculator doesn't understand the difference between negative 1 over 4 and 1 over negative 4. So those are actually different quadrants. They relate to different quadrants. If you took trig at some point, you talked about this, or if you've done polar coordinate conversions, you talked about this. So we're going to go ahead and graph. We've got about 1.5, and then it goes down about 3/8. So that's the point right there. So what we're looking at is this angle right here. That's our phase shift. Now that is, in fact, negative 14 degrees, so we're all good. This is very exciting. So now I can rewrite my original solution, although my original solution has nice, pretty, whatever you call those things, fractions. This is 1.55 cosine 8t minus a negative 14 degrees. So in fact, I have a plus 14. That means it is shifted to the left about 14 degrees. And that is this phase shift that you see up here. That 14 degrees is that phase shift there. The amplitude that you see here is that amplitude there. So this is a really, really useful way of figuring out how these things are actually going to look. I also know that 8 times the period is going to be equal to 2 pi. So the period is pi over 4. That means it's going to basically repeat itself every pi over 4, or I could say that the frequency is 4 over pi. Either way, that makes sense, but that also helps me look at, not this one, oops, that also helps me look at this distance here. This is a really, really awesome, whatever you call it, very, very awesome tool. Now, I'm pretty sure you're going to be like, oh my goodness, please, 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 can I do an example of something like this? Just to make sure I know what's going on. And the answer is, of course, I would never deny anyone the opportunity to do extra math problems. So let's take a look. We got this spring, it's 1 meter long and it's extended to 102 centimeters. This is great. All right, so we've got all kinds of unit problems. As you scroll through, you'll see that it once actually answers in CGS, which is centimeters, grams, seconds, like that. Great. So you just want to convert everything to centimeters and take it from there, but really the best thing to do right now is to pause the video, see how far you can get on your own, and then if you get stuck, then come back and review the video. So pause the video, see how far you can go, and I'll see you in a second. So we'll pretend that happened. All right, so we have our general format of our solution, which is that mx double prime plus kx is equal to some external force, but we don't have any external forces and I don't know what k is. However, I know that in equilibrium, delta L times k is equal to mg. Delta L is 2 centimeters, k is unknown, mass is unknown, and g is supposed to be 9.81 meters per second, but since I'm in centimeters, that means it's 980 centimeters per second squared. So 980. Meaning that k is equal to 490 times the mass. Alrighty, so I can do stuff with that. So mass x prime prime plus k, mass x equals no external forces. M's go away, so I have r squared plus 490 equals 0, so r is equal to plus or minus 7 square root of 10 I. Beautiful. If you didn't get this far, but now you kind of know what to do, pause the video, see how far you can get. So next, x is going to be equal to a cosine 7 square root of 10 t plus b sine 7 square root of 10 t. Beautiful, exciting. Now it said the object was displaced downward, so we do have some initial conditions. Its initial condition, it was placed downward 1 centimeter, and it was given an upward velocity of 14 centimeters per second. So I do need to take the derivative of this in order to apply that second initial condition. Negative 7 root 10 a sine this thingy. 7 root 10 b cosine this thingy. X at 0 was something. Negative 1, so A, x prime at 0 was 14, which is not going to be pretty. 0 plus 7 root 10b, meaning that b is equal to 2. No, that's silly. 2 divided by square root of 10. And Mama always said, never bring an irrational in the denominator to a party, because my Mama only has good taste when it comes to irrational numbers. 2 root 10 over 10, or root 10 over 5. Beautiful. So I have a lovely equation for displacement, which is negative cosine this thingy plus root 10 over 5 sine this thingy. So the question then becomes, how can I find the amplitude and the phase shift? All right, the amplitude is pretty straightforward. I know it's the square root of the sum of the squares. And I can do that. So again, if you've got this far, pause the video, or if you didn't get this far and you're just watching, pause the video and then see what you can do next. Remember, the best way to learn these problems is by actually doing them. If you're not doing them, it's going to be a lot harder to learn. Most of us learn by doing. There we go. Beautiful. Now for the tangent, or phi, is going to be the inverse tangent of the sine term over the cosine term. And I am going to go ahead and put this into my calculator. So I've got square root of 10 over 5, well, divided by negative 1, so thank you. That's exactly what I wanted. So I've got negative 32.3. Now it's really important though that I make sure this is exactly what I wanted. So remember, this is my y over x term. So the coordinate that I'm looking at is negative 1 and then something positive. So if I plot this, it's going to be negative 1, something positive. So the 32 degrees that I'm getting is actually this 32 degrees right here, which is not in the correct quadrant. So if I put in negative 32, that's actually a very, very, very wrong answer. So the way that I get this is I can say 180 degrees minus the 32, and that will give me the proper, let's do it that way. Come here. 180 degrees minus the 32. And that will give me the correct, well, I'll say this underneath that thingy. So I've got 148. So it's not 32, it's actually 148. So I can rewrite now my solution in phase amplitude form, which is root 35 over 5, whatever that happens to be. 1.18 times the cosine of 7 root 10. I don't care what that is as much because that's more of a frequency thing. And then minus 148 degrees. So what's really cool about this is if I have this now, I can actually plot this right away. So I know that cosine is normally supposed to look like this, but it's been shifted to the right 148 degrees. So it actually no longer looks like that. It's actually going to look like this, because I've actually, well, not quite past the 180, because this would be a 180 degree shift, so it's really going to be like here. So now it's going to look like this. And something like that. And I know the height is going to be 1.18. This is supposed to go all the way down. I'm just not very good at drawing backwards. So this is 1.18. So I can get the magnitude of the wave. So the highest it's ever going to be is 1.18. That's the maximum displacement I'm going to get. And I can see that the frequency is 7 root 10 times the period would be 2 pi. So the period would be 2 pi over 7 root 10, whatever that is. And then the frequency is 1 over the period. Now, again, since there is no damping going on in the system, this spring is theoretically going to go like this forever and ever and ever for all eternity. So we do eventually have to introduce damping at some point, but for the moment, we're pretty content with what we have here.